Ba-da-dum bum bum, you can go your own way. Okay, so what we got here are Intergalactic Chapter 16 problems, number 4 to 6, and here are the solutions for them, if you don't have the written work for it, or the written solutions. What we have for our first problem is two metal conducting balls are placed on a table, and they're also on insulating stands. So here's the ball and the stand. Here is an identical ball with its stand. We'll call this one ball A, and this one is ball B. We then take an insulated rod, so like a plastic rod, and we give it some negative charge by rubbing it with a fur rod, or with some fur. We then touch ball A, so the left ball here, with the insulating rod. Then, so what is the charge on ball A and ball B? And how did we arrive at our answer? Well, when we touch this negative rod to ball A, we are conducting electrons on it. The electrons that are on the rod want to push away from each other. They find some space on the left ball here, and it becomes negative. Some people might think that ball B is going to be positive or negative at this point, but actually, ball B is not going to have anything happen to it. It's going to be neutral. And the reason it's neutral is we have not conducted any charges onto it by touching it. And we also haven't inducted anything by, touching it with our hand, as we'll see in the next problem. If we wanted to be complete with this answer, though, what we could say is because these are close together and the A sphere here, A ball, is negatively charged, and this is B is a conductor, we could polarize this sphere, though. We could push the charges, these electrons, to the right, which would leave a lack of electrons on the left-hand side. This would polarize this sphere, but the amount of positive and negative charges would still remain the same, and therefore it would be net neutral. Okay, so that's the most complete answer that we can have. Now, in question 5, while close together, so we have the same kind of scenario from before. There's ball A, there's ball B. Here is the negatively charged ball A, and here is the polarized ball B, and that polarization is important now. Ball B is then touched by a clumsy physics student. So here's a student's hand. Their hands are made of green, and what this means is that this student is going to act as a ground here. What is now the charge of ball A and ball B? Positive, negative, or neutral? And how did we get there? Well, ball A is still going to be negative. It hasn't touched anything. It hasn't been touched by anything. So nothing has been conducted or inducted onto it. It's still negative. What will happen here, though, is when we look at ball B, because it's being polarized by ball A, when this clumsy physics student touches the ball, these electrons are going to try to escape as far away from possible. That's what these electrons are trying to do. They're trying to get away from sphere A. So they're going to run down the physics student and into the Earth. And these electrons are, bloop, they're gone. Okay? What will happen then is when the student releases this, because these electrons are gone, the sphere is still there. This ball B is now going to be net positive because the electrons ran away. Okay, they went into the ground, they went into the Earth. There are a number of different follow-ups you can do to this problem. If the clumsy physics student had their hand on the ball and they wanted to make sure that this stayed neutral, what could they do? Well, just by leaving their hand on the ball, they could just move them apart so that B was not being polarized anymore. And if B was no longer being polarized, then any of the charges that would have run away would come back through the Earth, back onto the sphere, and it would remain neutral. So if they wanted to kind of fix their little whoopsies, that's how they could do it there. Okay? So in this example, though, whenever they do touch it, because it is being polarized, A will stay the same as negative, and B will wind up positive through induction. Last but not least, we've got problem 6. We've got 2 point charges. We'll just say they're both positive. 1, 2, and they're sitting at 2 centimeters apart. Then the charges are moved 8 centimeters away. So a much, much larger distance. That's 8. What is the ratio of the force on the charges from the initial position up top to the final position in the bottom? Well, when we think about forces for charges, for point charges like this, we're thinking of Coulomb's law, which is K, Q, Q over r squared, their separation distance. And this is very similar to the gravitational force equation, GMM over r squared. And at this point, all we're trying to do is compare the initial values of the forces to the final values of the forces. KQQ over r squared. Now, in this case, K's are constant. That's Coulomb's constant, 9.0 times 10 to the ninth. Q1 is a constant, and Q2 is a constant. The only thing that's changing is this is some initial position. That's the 2 centimeters. And this is the final position. This is the 8 centimeters. So when we compare the initial force to the final force, what we're going to have here is 8 squared over 2 squared. Remember, this is the denominator, so it flips and becomes up top. And really, this is just going to say this is a similar thing to 4 over 1 quantity squared. I did 8 over 2, that's 4. Then they're both, well, I pulled the square out. I pulled the square out first, and then I divided 8 over 2. And in this case, we get 16. So F1 is, or the initial position, is 16 times greater than the final position. That's because they're so much closer together. Even though they've been increased in their distance only by a factor of 4, we went from 2 to 8, the force increases by the square of that. It increases by 16. And it doesn't actually matter that this is 2 centimeters and 8 centimeters. It could have been 1 centimeters and 4 centimeters. It could have been 8 centimeters and 32 centimeters. These still are just factors of 4 on the increase of distance, which means a factor of 16 increase on the force because it's that squared property, okay? And if we went from something like a little bit different, if we went from, I don't know, let's do 4 centimeters to 12 centimeters, well, that's an increase of 3 of the distance, which means that the force is going to increase by 9 because the square of 3 gives us that, okay? So that's how we just do a quick little ratio on that last problem. With that, there's problems 4, 5, and 6, 2 conduction-induction problems, and then a little Coulomb's law. And with that, we're finished. Take it easy. Adios.